Okay, so let's assume two people are pushing a stalled car as shown in this picture. The mass of the car is 1,850 kilograms right there. One person applies a force of 275 newtons, while the other applies a force of 395 newtons. This guy's a little stronger. Both forces act in the same direction. A third force of 560 newtons also acts on the car, but in a direction opposite to that which the other people are pushing. The force arises because of the friction and the extent to which the pavement opposes the motion of the tires. Find the acceleration of the car, right? So this is a Newton's second law problem. We've got to figure out the acceleration of the car. We've got an equation here, sum of the forces divided by the mass equals the acceleration. This is how the AP Physics 1 formula sheet shows it, so this is how I'm going to refer to it. Though classically it's sum of the forces equal mass times acceleration. So this is how we're going to refer to it, though, and I think it's honestly better this way in some sense. So, okay, the sum of the forces. So we've got let's go ahead and sum the forces. We're just dealing with one direction right now, which is the x direction. So we're going to say sum of the forces in the x direction equal, and that's 275 newtons, right, plus 395 newtons. And then we're summing, so I like to put add and then a negative 560 newtons because it's in the opposite direction, right? So add these up, right, on a calculator, and you're going to get that the sum of the forces in the x direction equal 110 newtons. All right, so if you add these together and then subtract the 560, you'll get 110. The acceleration of the car is equal to this, and the mass of the car, right? Mass of the car is 1,850 kilograms. So we've got the sum of the forces, we've got the mass, we can plug it all in and find the acceleration. So 110 newtons divided by 1,850 kilograms equals what? And we know the units of acceleration are meters per second squared. So it's going to be in meters per second squared. Let's take a quick aside to figure out why it's meters per second squared. So I'm going to actually add a page. Well, I guess you probably hate when I do this. Let's calculate the number and then we'll get it at we'll take an aside to figure out the unit. So it was 110 divided by 1850. You get that that's equal to roughly this, so 0.59, we'll round it there, 0.59 meters per second squared. So 0.59, if I could find where here we go, 0.59 meters per second squared. Okay, now let's take our aside and figure out why it's meters per second squared. Like, how do you get that from Newton and kilogram? There's no meters, there's no second there. Okay, so let's look back at what the classical physics Newton's second law is. So they're not different. I'm just rearranging the first equation. So if we take sum of the forces over mass equals acceleration, right, then we can multiply both sides by mass and get that the sum of the forces equal mass times acceleration, and we can plug the units in for that. So mass has units of kilogram, and acceleration is meters per second squared. So kilogram times meters per second squared are equal to your units of force, right? Which we already know from the previous problem is Newton. So this, Newton, is what's equal to that. So our force is Newton. That's an arrow. About as good as one as I can draw, I guess. Newton is a kilogram times meter per second squared. So if you ever see Newton divided by kilogram, this will give you meters per second squared, right? Because kilogram is what kilogram meter per second squared is what we said a Newton was, divided by kilogram. Kilograms cancel, and you get meters per second squared. Now, Newton is a lot more convenient to write than kilograms meters per second squared because it comes up a lot in physics. They came up with a unit for it called Newton. So, what you need to know is that Newton is not the fundamental unit. The fundamental unit is kilogram, meter, second squared. These are things that cannot be reduced further, right? So mass, length, and time, these are fundamental measurements, and you cannot reduce these things further. Okay. I'll see you in the next video.